The next topic is intervals that you can calculate from a linear regression model. But actually, we're going to first go back to a simpler context, not linear regression, to give ourselves a basis for moving on to intervals for regression. So here's a scenario you've seen before. We have some population that maybe looks like this and has mean mu and variance sigma squared. And we're going to draw some y values from that population distribution. Okay, so you've seen this lots of times before. So maybe we have a sample size of n, right? That's a lowercase n, where each of the n observations is a draw from this normal distribution with mean mu and variance sigma squared. I'm assuming I have independent sampling. And you saw this when we did the central limit theorem, that if we repeatedly sample from this distribution and write down y bar each time, this is the distribution of y, the distribution of y bar will also be centered at mu, but will have a smaller variance, right? And in particular, we showed that y bar will follow a normal distribution centered at mu, but again, with a smaller variance, the variance will be sigma squared over n. So this is something we've seen before, right? And we did this in the central limit theorem simulation, but note that actually, if you know for sure that the initial population distribution is normal, you don't even need to have a big sample size in order for this to be true. If the population distribution is normal, then y bar follows a normal distribution as well. Again, even without having to make any claims about a large sample size. Okay, so why am I talking about this? Well, I want us to remember what we do when we calculate an interval in this context, right? So we calculate a 95% confidence interval for the parameter mu, which, by the way, is equal to the mean of y in the population. That's just what it is, right? How do we calculate it? Well, we take our estimate of mu, which is y bar, and we add or subtract 2 times the standard error of y bar. In other words, the square root of the variance, or the estimated square root of the variance of y bar. So our confidence interval is, I'll make this an arrow instead of an equal sign. Our confidence interval is y bar plus or minus 2 times the square root of s squared over n, right? So this thing here is a standard error of y bar. Where did I get it from? Well, here's the variance of y bar. So then s squared over n is the estimated variance of y bar, and the square root of that variance is the standard error of y bar. So this is something you've seen. Again, this is a 95% confidence interval for the mean, and the idea is that this interval has a 95% chance of covering the mean. So if you have a data set, let's imagine a data set where I want to draw it. Maybe I'll draw in this corner. Okay, so imagine we have a data set. So this is my actual data. Now here it is. Here's a histogram of my data, right? It's centered around some value, y bar, that's the mean in my data set. And I come up with some interval, like a 95% confidence interval for mu, which is going to be y bar plus or minus something, right? And the range of that confidence interval is going to be usually much smaller than the range of the data itself, because again, its variance is sigma squared over n. I'm estimating with s squared over n. I'm not trying to tell you where all of the data lies, but rather give you an interval for where the mean lies. So just to tie this to the example we talked about earlier in this class about heights. Suppose I sample 100 Wellesley students and observe that their heights go from 5 feet to 6 feet, but that the mean was 5'5", then I may make a guess that the mean of all Wellesley students' heights is somewhere between 5'4" and 5'6", right? That's the kind of interval we're talking about here. Here's something we didn't do earlier, and we didn't because it's not that common to talk about it, but it's what we need in order to make a nice connection to the linear regression case. Suppose that I'm not actually trying to learn about the average height of all Wellesley students. My quantity of interest is not actually mu. That's not what I'm doing. Suppose that the reason I collected 100 Wellesley students and measured their heights is that when a new Wellesley student shows up, I want to be able to make a guess at where her height probably lies. In other words, I want to produce a range of values an upper bound and a lower bound, such that there's a 95% chance that a new Wellesley student's height will fall in that range. Why might I be doing that? I don't know. Maybe I'm like making new beds or doorways or something, right? I guess that would be very inclusive if I'm excluding people who are very tall or very short, right? Maybe it's something less consequential than a bed or a door. Maybe it is whether, like the heights of the computers in the computer lab, and I want people to be able to see over them, but I also want people to be able to see around them, etc. Okay, so for whatever reason, I want to come up with an interval such that when a new Wellesley student walks in the door, there's 95% chance that her height falls in a particular range. Okay, now that's not the confidence interval. That's the main thing I want you to see right here. The idea I just described is not the confidence interval. The confidence interval is a range of values such that we think there's a 95% chance that this interval covers the true population mean. So the more data I gather on Wellesley students' heights, the more students I sample, the narrower that interval will get. And I say, oh, I sampled 200 students. Now I think that the average height must be between 5'4.5" and 5'5.5", right? That's where I think it is. But that confidence interval is about where the mean of all the heights lie. If a new Wellesley student walks in the door, I don't think that her height is necessarily between 5'4" and 5'5", 6", if that's my confidence interval. Her height probably lies between 5 feet and 6 feet, like everybody else in my sample. There's a big difference between a confidence interval that's trying to estimate where a parameter, like a mean, might lie, and a prediction interval. That's the new term here. A prediction interval for a future value of y. The prediction interval will typically be much wider than the confidence interval. The confidence interval says, here's where I think the mean of all the values in the population is. The prediction interval says, here's a range that's wide enough that 95% of the population, I'm guessing, would fall in this range. That the next person who walks in the door has a 95% chance of falling within this range. So let me redraw this picture just so I can, it's supposed to be the same histogram and the same y bar, right? But now I want to make a prediction interval. Well, if somebody else walks in the door, I want to come up with the interval such that I think that there's a 95% chance her height falls in that range, right? Again, it's got to go pretty much from 5 feet to 6 feet if I want there to be a 95% chance that the next Wellesley student's height is going to fall in that range. So how do I come up with that interval? Well, I take y bar plus or minus 2 times, but now it can't just be the standard error of y bar. Now it's going to be something else. So it's going to be the square root of, well, I'm going to include the s squared over n that I had before, right? But I'm going to need something else. So let's understand why this s squared over n is in there, and then we'll understand what the something else has to be. So this s squared over n is an estimate of the sigma squared over n, which is the variance of y bar. It's the amount that y bar varies over lots of possible samples that I could obtain. So if I'm making a prediction interval, I'm trying to make a guess about where a range such that the next student's height will fall in this range. One of the things I have to take into account is that I'm not even totally sure what the overall average height is, right? So my new prediction interval is going to be centered at y bar, my best guess at the mean, but I have uncertainty about that guess. So the fact that this s squared over n is part of the calculation of the width of this prediction interval reflects the fact that I have uncertainty about, let me write this in words, how close y bar is to mu, right? So I'm making an interval that's centered at my best guess at the average height of all Wellesley students, but my best guess is based on my sample of some Wellesley students, and I have some uncertainty about how good my guess is, my best guess at the mean. So the fact that s squared over n is within this square root here, is part of this calculation of the width of this interval, is because I am not sure how close y bar is to mu, or at least I have a sense that y bar has a variance of approximately s squared over n about mu. Okay, so if I left it at just s squared over n, now I'm back to this confidence interval up here, right? That tells me about how much variance y bar has. But the distribution of my data, an actual student's height, follows a normal distribution centered at mu, which is what y bar is estimating. But the students' heights vary with a variance of sigma squared around that average height, right? So whatever the height of Wellesley students, whatever the mean height of Wellesley students is, Wellesley students' actual heights vary about that number with a variance of sigma squared. So the variance of my prediction interval needs to include not only my uncertainty about where the mean is, but also it needs to include my best guess at the variance of the heights themselves. So this right here is the variance, or let's see, the estimated of y values given mu. So suppose I knew the population mean, given the population mean, right? So I'm looking over here now, given the population mean, given if I knew that the population average height was 5 feet, the amount by which students' actual heights vary about that is sigma squared. That's what this S squared is estimating. S squared is an estimate of sigma squared. In addition to that, when I'm making this prediction interval, I don't actually know what mu is. So I also have this uncertainty about how close my guess of y bar is to mu, and that's this S squared over n. So this thing is a prediction interval. Know that the prediction interval will be wider, much wider than my confidence interval. Right, so let's write down a couple. So make sure you make note of what I just wrote here, but now we'll go to a new slide and write down some facts. The prediction interval will be wider than the confidence interval because the actual data points vary around the mean. Right? So again, if I just ask you, give me an interval such that based on your knowledge of the world, there's a 95% chance that the average Wellesley student's height, the mean of Wellesley student's heights falls in that range, you're going to give me a narrow interval right around 5.5. If I say give me an interval such that there's a 95% chance that the next Wellesley student who walks in the room will be in this range, it's got to be a way wider range. And that's the difference between a prediction interval and a confidence interval. Another fact that implies is that as you gather more data, so as the sample size increases, the confidence interval's width will shrink a lot. In fact, it'll shrink to 0 as the sample size goes to infinity. The confidence interval's width will shrink towards 0. Before I write the rest of this phrase, let me make sure you see what that means. If I gather 100 Wellesley students and I use them to create a 95% confidence interval for height, I might again get 5.4 to 5.6. If I get another 100 Wellesley students, now I have a total of 200 Wellesley students that I've collected data on. I look at their heights, now I might have an interval of 5.4.5 to 5.5.5. If I gather the heights of 1,000 Wellesley students, now I'm going to have a really narrow interval around 5.5, and 5.5 is the right answer, right? It'll be like, 1/8 of a centimeter, no, I'm talking about inches, 1/8 of an inch below 5.5 to 1/8 of an inch above 5.5, right? If I gather information on the heights on all of the Wellesley students, my sample size increases all the way to the population size. Now I don't have even a confidence interval anymore. My uncertainty is equal to 0. I actually just calculate mu and provide that one number. The confidence interval's width decreases as the sample size increases all the way down to 0 when the sample size is equal to the population size. And so just to note that here, right, we're talking about this interval. If n is equal to infinity, right, if the denominator is equal to infinity, then the thing you're adding subtracting is equal to 0, right? And in that case, y bar is actually equal to mu. Okay, so for the confidence interval, as the sample size increases, the confidence interval width will shrink all the way to 0. but the prediction interval will still be wide. No matter how many Wellesley students you sample and gather data on, if I ask you to predict the height of the next Wellesley student who walks in the door, you still might think that her height falls somewhere between 5 foot and 6 feet. Just because you gather data on 1,000 previous students does not imply that the next student who walks in the door will have a height of exactly 5'5", right? I might gather data on 1,000 students, look at their heights. The mean of their heights might be very close to 5'5", and the range of their heights is 5 foot to 6 foot. And the next person who walks in the door may as well be somebody who's 5'11". No reason that that wouldn't happen, right? The prediction interval will still be wide enough to encompass the whole range of data points in the population. In fact, the more data you get, the better job the prediction interval will do covering the range of the entire population distribution, or 95% of it, right? But if, as the sample size increases, your certainty about where the mean lies becomes higher and higher. The confidence interval's width goes to 0, but the prediction interval's width does not go to 0. And we can see that in the formula for it. If you look here, suppose that n goes to infinity, then this term here is equal to 0, but this thing's not equal to 0. This is still just the sample variance that you calculate. So the width of your interval, your prediction interval, does not go to 0 when the sample size goes all the way to the population size.